Hello Calculus 2 fans, going to continue my series here where I talk about preparing for our exams. We're going to be talking about these three sections. This is something I'm having my class do in their quiz sections, and the goal is just to get you ready for exams. This is integration by parts. This is trig integration, the second one. And this is trig substitution. Three of the biggest integration techniques. These two are very specialized but important for certain cases. Integration by parts is a general method. So I'm just going to focus on some examples of each and then pull it up in my exam archive. I haven't prepared yet. We're going to work through the problems. Hopefully you can work through them with me. And then I will go look at the solutions, make sure we didn't make any silly mistakes, but I'm just trying to get ideas down. So I start off with this. This is a trig integral. So this is from section 7.2 of our textbook. But there's a set strategy. And as I talked about in class, the strategy is everything is substitution. Basically clever substitution. Unless all you have is even powers. Of sine and cosine. And then we talked in class about how to deal with that using half-angle identity. So in this case, we have an odd power. And so we're going to set up a substitution. And the entire strategy was this. You basically, in order for it to set up a substitution, you need two things. You need to choose u and you need its derivative. So the interesting thing about these problems is the first thing we're going to do is we're going to make the derivative appear. And the derivative that we're going to make appear is sine. And the reason I know we're going to make it appear because that's where this odd power is. So the moment I yank that out, this is going to become sine of x dx. I'm not actually yanking out, I'm just factoring. Sine cubed means 3 sines multiplied times each other. So if I factor one out, it's going to be sine squared. And there's still going to be this cosine to the fourth. So as I talked about in class, if you understand the ideas of this section, there isn't a lot. It's not too bad. We've basically made this derivative appear. Now we'd like to change everything else into cosines. Now, if I want to be precise, if I say cosine here, then the derivative is negative. This is the loveless law of the C's. If you take a derivative of something that starts with the C, the derivative is negative. Cosine, cosecant, cotangent. Anyways, so we will have to account for that. I like to think of it this way. I just move the negative one to the other side. And so this is the one, you gotta be careful of signs always. That's gonna become this. This is the whole idea. We dealt with that first, but then we see what the problem is. The problem is, yes, I can call this u to the fourth, but what am I gonna do with the sine squared? And we have a clever little bit, not clever, just a key idea, which is that cosine squared of x plus sine squared of x is always 1. That's the most important identity about sine and cosine you're ever going to encounter. But in this situation, it gives us a way to turn something from a sine squared to a cosine squared. And this is why it's so important that this is an odd number, because if you subtract 1 from an odd number, it becomes an even number. And if it's an even number, we can use this. If it happened to be, you would use it over and over again. But this right here is 1 minus cosine squared. Which means it's 1 minus u squared. Success. That's the main method of this, except if it's even powers of sine and cosine. Now, if you're one of my students, you know that I prefer to change the bounds as I go because it just makes things way easier. So let's do it. I'm going to plug in a 0 here. Cosine of 0 is 1. I'm going to plug in a pi over 2 here. Sine of pi over 2 is 0. This happens sometimes where it looks like this. Yeah, someone who kind of is familiar with this would say, oh, there's a negative. I could really make this. I'll do it in 2 steps if you want. Negative, this is not required. I am going to distribute minus u to the 6th. I talked in class about how one of the common errors here is exponent rules, but u to the 4th times u squared. You can actually just play this silly counting game. There's 4 of these. There's 2 of these. 1, 2, 3, 4, 5, 6. The rule is to add. Anyways, people who know calculus would flip this just because it looks prettier. Is it required? No. And then we can finish it off. So I'm going to have 1/5 u to the 5th minus 1/7 u to the 7th from 0 to 1. So it's going to be 1/5 minus 1/7. Now that's what you get when you plug in 1, but when you plug in 0, you get 0 minus 0. 1/5 minus 1/7. Let's see, that's going to be 35 over... So what am I saying, 35? My brain was working backwards there. So 35, 7 over 35 minus 5 over 35. So my final answer is 2 over 35. Okay, the main ideas are this. It's odd, you factor 1 out, and you change everything else to cosines. So you can see I didn't have to look anything up. I just think about, there's the derivative. But if I want this to be out, then I need everything else to be cosines. That's how I remember. I don't have to look in a table. This is winter 2015. I like to peek. And if you're in my class, you should be scrolling down to exam 2 now. Winter 2015. Let's see if I did something silly. Also, my purpose here is to show you other exam questions. There's an integration by parts. There's a partial fractions. We don't know that yet in my course. This is a trig sub with a complete the square. That's kind of as big as they get. And this is the question we just did. 2/35. Yay! We got it. Okay, so let's keep going. So then we encounter this. And if you understand the ideas, you can think through, well, what are my 2 substitution options? One option is to do tangent of x. Another option is to do secant of x. Those are the first things I would think about. But if I'm going to do tangent, the derivative is secant squared. And if I'm going to do secant, the derivative is secant tangent. Both techniques might work. In fact, they do. Both techniques work here, and then I look back at it. So let's just look at them. Let's look at this one, and then we'll look at this one, just so you can get a little comparison. If I was trying to use this technique, my first step would be to pull out a secant squared. So that would look like this. Secant squared of x, tangent cubed of x, secant squared of x dx. Success. And then I'd be trying to change everything else into a tangent. So that's approach 1. Approach 2 would be to pull out a secant tangent. So maybe I'll put that over here. Approach 2. And on a test, you wouldn't do both. You would just do one. If I take out one secant, there's going to be a secant cubed left. If I take out one tangent, there's going to be a tangent squared left. And that's going to be secant tangent. Okay. So then you go, well, how am I going to... I mean, even if you forgot the idea, I always think, even if you knew the general overarching principles here, you would know that this is going to be u cubed. You would know that this is going to be u cubed. Again, try to separate. I'm sorry to do these side by side. That might be confusing you. So over here on the left, I'm using that. Over here on the right, I'm using this. And again, you don't need to do both, but you can see the issue. The problem here is that I need to turn everything into a tangent, and this is not a tangent. So you go, hold on, that's a different identity. It is. I can tell you that when I was a student, I didn't have this memorized. I do know what it is now because I've used it so much. But I've always had this memorized because this comes from the unit circle. So at some point along the way, an instructor told me, what if you divide everything by cosine squared of x? It gives you an easy way to remember the other identity, the equivalent identity for secant and tangent. Because this would become 1 plus tangent squared equals secant squared. That's how I always remember it. So in this case, I'm trying to get rid of secant squared. So secant squared is 1 plus tangent squared. So then we got it. Sorry for that. 1 plus u squared. Done. And in my opinion, that looks like it's going to be a little faster, but it's about the same. This is going to be u to the 5th. Again, if you forget, you count. 1/4 u to the 4th plus 1/6 u to the 6th plus c. So it's 1/4, and this is when u is tangent. That's one correct answer. Often in these problems that involve trig, there are many correct equivalent answers, simply because there's so many ways to write a trig function. All right, let's do this one. Again, there'd be no reason to do both. So we just said that tangent. So we said that 1 plus tangent squared is secant squared. So that means tangent squared is secant squared minus 1. And in this case, I'm changing everything to the left of this to secant so that I can set up that substitution. This is going to be u squared minus 1. When I distribute, it's going to be u to the 5th minus u to the 3rd du. It's going to be 1/6 u to the 6th minus 1/4 u to the 4th plus c. So it's going to be 1/6 secant to the 6th of x minus 1/4 secant to the 4th of x plus c. You say, well, those answers don't look the same. If you were to graph those two functions without the c, they're either going to be the same or they're going to be horizontally shifted, but they have the same slopes everywhere. Let's look, though, to make sure I didn't do something silly. Winter 2011. Winter 2011. Solutions. Oh, I only did one of them. Oh, I did the weirder of the two, in my opinion. I don't know why. Nowadays, I would have done both, but that matches. But the other one is fine, too. Okay. There you go. So that's the... We didn't do an even power of sine and cosine, the only thing I'm missing there. But that gives you the principles. 80% of the time, that's what you're doing. There are the situations where there's an even power of sine and cosine. And that is an important case. I just didn't have one in this test prep. Okay, now let's do some 7-1. So now we're going to jump to integration by parts. Integration by parts is good for logs, inverse trig, and products. And I gave examples of all those in class, and I just basically said it's really a handful of things. If you can use something else first, a substitution or a simplification, do that. But if you've thought of that already and nothing really fits, and there's a log, do integration by parts. Now, a calculus student, this is pretty, but a calculus student would write this way. Calculus students write things in an ugly way, but it makes it easier to apply our rules. So when I look at this, I see this is the integral. That's just to help you see it. And so the moment you decide you're going to do integration by parts, you want to be organized, you want to do it the same way each time, you want to build up a good routine. It's just this formula. It's integrate. So we talked in class about where it comes from, how it comes from the product rule, how we're just rearranging. But you have one choice to make, which is what goes here. After you make this choice, this is going to be the rest. And you're going to take the derivative, you're going to integrate, and you're going to plug in. That's the whole method. So there's really one choice to make. I talked in class a little bit about this silly idea of lipits. Lipit. Just one of many acronyms people have come up with where you pick u higher. So in this case, I was given a log, and I was given a power of x. So pick u higher on the Lipit scale. So you basically don't even have to think now. This is log of x. That means this has to be the rest. You take the derivative. You integrate, so the power is going to go up 1 over -4. And then you're off to the races. So we're going to smush these two things together. uv. That's what this is. So this is going to be -1/4. And now I'm kind of tempted to make it look nice again. That's x to the -4th. It's going to be log of x, x to the 4th. And that's not necessary, but I always say I smushed those two things together in whatever way it looked pleasing to me. And then I'm going to do minus the integral, and then I'm going to smush these two things together. That's this. So if I was doing it, I would clean it up right now. I would have -1/4. I'd have 1 over x to the 4th, and I'd 1 over x dx. So I would just write -1/4, 1 over x to the 5th. And then I would simplify, and there is a place, there's a lot of negative signs when you're doing integration by parts, so there is a moment where you have to stop here. The formula itself does have a negative, and the antiderivative had a negative, so it's going to be plus 1/4. And now I'm going to rewrite it to do some calculus. And so I get -1/4. And this is a fairly formulaic method. It's not too bad, but it's something you need to practice. Plus c, so altogether I get negative log, if I was going to write this pretty, log of x over 4x to the 4th minus 1 over 16x to the 4th plus c. And I probably could think of many other ways to write that, but let's go look at fall 2017. And I'm partially doing this just so we can look. Okay, we don't know this first problem yet. That's what 7.4 will be about. Hey, look, there's an integration by parts with inverse trig. And notice how we picked the inverse trig, and then the rest was this. The inverse trig is the I and the Lipit. There's a trig substitution, that's 7.3. Here's the problem we just did. Looks like I factored out the -1, but that doesn't matter. This is all acceptable. There you go. Let's keep going. Okay, now we have a question that asks about average value. It's not really about average value. It's about integration by parts. But if you've forgotten, average value is this. The integral from a to b of f of x dx. And so this question was asking you to do 1 over 1/3 minus 0. The integral from 0 to 1/3 of arctangent of 3x dx. 1 over 1/3 is just 3. So we're doing 3, and then we need to do the times the integral of this. And I kind of have one, I have one thought here. Because of the 1/3 and 3, that maybe our life would be easier if we did a substitution. This is a bit of a, if you didn't see this, it doesn't matter. You could continue. And I'm using a 3 instead of, a t instead of a u because I anticipate we're going to do a little more. But this is just a house cleaning thing. So when I plug in a 0 here, I get 0. When I plug in a 1/3, I get 1. So 0, 1. And this is going to be 1/3 dt. Ooh, and then the thirds cancel. And this is something I talk a lot about in my class, is how if things are a little complicated, you might try a substitution just to make it look nicer. Is that necessary? No, but I'm sort of happy that from here on out I just have to compute this. Okay, so now I'm going to engage in integration by parts. I'm going to set up my template. I'm going to pick u, and then the rest I don't really have to think about. How do I pick u? I want to choose the thing that I can take the derivative of, which in this case is they gave me an inverse trig. And that's all that's there. And so you have to put it here because there's no other way forward. This means this has to be 1 dt because that's the rest. You integrate this, you get t. You take the derivative of this, you get t squared plus 1. And so then this becomes, you smush those two together, t arctangent of t from 0 to 1 minus the integral from 0 to 1 of t, t squared plus 1. So now we have a couple smaller jobs to do here. One is just calculate, and you can wait to do that or do that now. This calculation is not so bad. If you plug in a 0, you get 0. If you plug in a 1, you get arctangent of 1. Arctangent of 1 is one of those values we want to know. I'm not going to do a review on that right now. So it's just going to be pi over 4. This integral then becomes a new challenge. And it's not in our table, but there's something we have to see, and it has to do with these two things. Substitution is going to work. Now you can kind of see why I like to use t at the beginning of a problem, because if I'm just using a t to clean things up, I might want to use a u later. Dt is 1 over 2t du. And so this is going to become, let's write down everything. Pi over 4 from there, minus, and then this is going to become 1, this is 2. I'm just plugging into the substitution. T over u, 1 over 2t du. Success. Now I got it. Pi over 4, zoom up a little bit. Pi over 4 minus the log, half of the log of u from 1 to 2. Log of 1 is 0, so I think all you get is pi over 4 minus a half log of 2, which there's lots of ways I could write that. Okay, what was that exam? Fall 2011. Am I still in there? No, this is a different one. Fall 2011. Maybe I mismarked it. Well, shoot. We're not going to be able to check it. Fall 2011 3A. Maybe I meant winter 2011. Darn it. Sorry about that. It is winter 2011. Okay, there we go. Done. Let's try another one. This one makes this suggestion. Now, once we get to section 7.5, we'll talk about this a little bit. But this is another cleaning up suggestion. There's kind of an interesting, I don't know if it's a trick, but way to make your life easier, which is to first solve for x and then take the derivative. You get the same thing as if you'd have taken the derivative directly. And then rearranged. And sometimes students say, well, those aren't the same things. But indeed they are, because the square root of x is t. Okay, so let's plug all this stuff in. This becomes cosine of t. This is 2t dt. And then I go, oh, this looks like a typical integration by parts. I need a u, I need a dv, du, v. We have a power of x, and we have a trig. Power of x, trig, derivative, integrate, smush those two together, so 2t sine of t, minus the integral, smush these two together, 2 sine of t dt, so we have 2t sine of t, and derivative sine is negative cosine, and there's that negative, so it's going to be 2 cosine of t plus c, and then replacing 2 root x sine of root x plus 2 cosine of root x plus c. That's winter 2019. Let's take a look. Winter 2019. So we have a trig substitution, we have a partial fractions, we have another one of these integration by parts with a log. We have one of these, oh, it looks like I did that one both ways. That is the same as the problem I did earlier, but that time I did it both ways. And then we have this one we just computed. Okay, so there's integration by parts. We had a log, we had an inverse trig, we had a product. So there's them three main situations you encounter. Okay, lastly, we get to this topic of trig substitution. Trig substitution is a real clever method for dealing with things that have square roots in a square, and they boil down to just one really key observation, which is that this is the same thing as cosine squared. This tangent squared of x plus 1 is the same thing as secant squared. And it's funny because you don't see any trig here. So this is a very clever method. Secant squared minus 1. And the truth is, these are hard integrals to do, but there is a way to turn them into trig integrals by using these identities. And that's basically what we're going to do. So in this case, when I look at it, there's a square root hiding in there. So basically, I really want to simplify the square root of x squared plus 4. And so when you notice that, then the challenge becomes, how can I simplify that? Because it doesn't distribute. We call it the sophomore's dream, where you distribute this and call this x plus 2. Unfortunately, that's not true. They're not the same at all. They're not even close to the same. But there is a way. And the way is to look up here and say, which one of these three identities looks like this? It's this one. And so we would like to put a tangent here and end up with the tangent squared plus 1, but we're not going to get a plus 1 because of this 4. And so we do the following. We're going to replace x with tangent. And we're going to put a number in front of it, and that number, when we square it, we want it to be 4. So it's 2. So this is the technique that basically when you see this, you do this. Whenever it's a plus, there's a quadratic under a radical, and then that should get rid of your root. So let's go through, and there's several things we then have to do. It's a trade-off. So first off, the whole reason we do it is because of what's going to happen here. So let's talk about that first. This is going to become 4 tangent squared of x plus 4. And this then is going to be the square root of 4 tangent squared of x plus 1. And this is the same as 4 secant squared of x. And this is the same as 2 secant of x. Now there's a little subtlety here, only if secant of x is positive. Now if there are no bounds, you don't have to think about this. If there are bounds, you might have to think about what domain you want to use. We don't really focus on that as much in our problems, but there is a little subtlety, because technically there should be absolute values here. But if you don't have any bounds and you're not talking about whether things are positive or negative. So there are things to discuss, but I'm going to point you to your textbook for that. So that's one thing. That's what this square, and if you say, I didn't see a square root there, it's there. It's like this. It was just hiding a little bit. Okay, so we just figured out that this substitution will completely rid us of the square root and make all of that 2 secant of theta. Unfortunately, that's still going to be cubed. And now we got to deal with some other changes. The top's going to become 4 tangent squared of theta. So I've substituted that in here. And then lastly, and this, for some reason, I think just in the middle of doing the rest, students tend to forget this, but you do have to remember the derivative. Secant squared of x dx. So it's going to be 2. And that's actually the method. The method is that idea that if we make this substitution, the square root will go away. But then we have to face the consequences. Okay, so what are those consequences? In this case, we have, it's going to be 4 tangent squared of theta. It's going to be 8 secant cubed of theta. And then there's going to be a 2 secant squared of theta. So I think those two, that all cancels because it's going to be 8 over 8. And I think 2 of the secants cancel. So we're going to have tangent squared of theta over secant of theta. That's the substitution step. And as I said, these problems tend to have 3 main pieces. The substitution step, and then you do a problem from 7-2, the trig integral. And this is where you're going to have to remember the methods from the last section. And there might be more than one way to get there. Now this one's sort of weird because it's a fraction. And so your options here are to turn everything into sines and cosines, option 1. Another option is to use your identities to see if you can simplify it. Now, looking at it, I think both those options are pretty good. If you turn everything into sine and cosine, yeah, that's okay. But I'm really tempted to use identity because I have that tangent squared on top. And so I'm really tempted. So this is the challenge sometimes of these. Tangent squared is secant squared of x minus 1. Oh, why did I do that? Secant. So wait a second, we can simplify that. That's going to become secant of theta minus 1 over secant of theta. And 1 over secant of theta is cosine of theta. Those are both in our table. Now the integral of secant is something we added to our table of known integrals in this section. I believe it's the log of secant of theta plus tangent of theta. It's not something I use every day. And then the other one is the antiderivative of cosine, which is sine plus c. And on my, just for anybody watching this video, you know, on my materials page, I have the test prep if you ever want to attempt it on problems like this on your own. But I have my Calculus 1 and 2 fact sheet. And that has, at least at UW, every derivative. This is something I made years ago. Every derivative that appears in our homework and every integral that appears in our homework. So here's that secant. It is the log of the absolute value of secant x plus tangent x. Okay. So then there's this third step. And the third step is how do we properly return to x? And what we know is that x equals, let's use a different color. First all arrays. X equals 2 tangent of theta, which means tangent of theta is x over 2. This gives you a ratio of 2 sides of a right triangle. We're going to use a right triangle to sort of help us think through what the other ratios would be. This is going to be opposite over adjacent. So I'm going to draw a triangle that has this ratio. And I'm going to solve for the other side. But that's fairly quick to do. It's the square root of 2 squared plus 4. So now we want to get, now I could talk about that, but I'm trying to be a little quicker. We want to get, this video is already way too long. We want to get sine of theta. That's what this is. We would like to get secant of theta. That's what this is. And we would like tangent of theta. Now tangent of theta we already know. It's opposite over adjacent, so it's x over 2. So this is x over 2. And we didn't really need the triangle for that because that was the one we already knew. Sine of theta is opposite over hypotenuse. So that's x over square root of x squared plus 4. And secant of theta is 1 over cosine. Cosine would be 2 over adjacent over hypotenuse would be this. Secant would be the square root of x squared plus 4 all over 2. And so now we can give our nice clean answer. Square root of x squared plus 4 over 2 plus x over 2 minus x over square root of x squared plus 4 plus c. Whew. So those are the 3 steps. You do the substitution, you do a trig problem, and then you do this triangle trick. It's these 3 independent things. So that's fall 2017. Let's go take a look. Make sure I didn't do anything silly. Fall 2017. While we're looking, we'll tour through this exam. We have a partial fractions, which is 7.4. We haven't done that yet. Integration by parts, I think I already talked about that. And then this problem. Oh, a funny little thing is I talk about how you could simplify the log, but there's no need to. Okay. One big problem here. Let's zoom in and then we'll finish this video. So here we have one that's similar to the last one, except that it has this darn middle term. And that adds sort of a degree of difficulty. It makes the problem a little bit longer. This is the longest type of problem we have all term. And this is about completing the square. Now, sometimes I tell students, if you don't remember how to complete the square, just do an example of a perfect square over here. And realize that there's going to be a 36, and there's going to be an x squared, and in the middle there's going to be a 12. The idea of completing the square is usually what happens is you don't know this number and you don't know this number. And you'll have to somehow figure out what they are based off of the fact that you do know this. Well, I always just remember, okay, if it's exactly like this and there's a 1 in front of x, there are more general methods for if there's not a 1 in front of x. But rather than learn those, I'm going to keep things simple. Just make it so there's a 1 in front of x. Factor out a number if it's there. Then do half of your middle term, which is 6, and then square it. So I'm going to do half of the middle term, which is 2, and then square it. So I would like there to be a 4 here, but unfortunately there's not a 4 there. So we do this goofy little thing. We're going to subtract 4 from the 13. So all we're doing is rewriting it so that we have a perfect square. And then we ask ourselves, in order to make it a perfect square, what number's left over? So it's x plus 2 squared plus 9. And that's it. I always then immediately re-expand because I don't trust myself. So I would write x squared plus 4x plus 4 plus 9. Is that the same as what we started with? Yes. That's the completing the square idea. It's not too bad, but you should make sure you have it, make sure you have it right, and then we're going to restart the problem. What do I mean by restart the problem? So we have the integral x over, and that's going to be x plus 2 squared plus 9. Then I have this square root, that 1/2, and then I have cubed. Okay. Some students tell me that they like to do a substitution so that this doesn't look so gross. So let's do that. Let's do t equals x plus 2. That means dt is equal to dx. And that means x is t minus 2. So that means we get this integral. T minus 2 on top. T squared plus 9 to the third dt. And now it looks more familiar. Okay, so now we can say, which one will give me this identity? Which identity has the plus? It's the tangent one. Oh, I didn't mean to have two problems with the tangent. That was accidental. Tangent of theta. That means that where the derivative is going to be 3 secant squared of theta. It means that the square root will look like this, 9 tangent squared of theta plus 9. And when we factor out the 9, it's going to be the square root of 9 tangent squared plus 1, which is going to be secant squared. This gets a little faster. I mean, you do want to write some of these steps, but it's going to be 3 secant. So when I look at this, I see that the t is going to be 3 tangent minus 1. The denominator is going to be 3 secant, and that's going to be cubed. The dt is going to be 3 secant squared. This is pretty similar to the problem I just did. I didn't realize that they were so similar, but it's going to be 3 tangent of theta minus 2. I randomly grabbed a few questions. That was not intentional. When I'm making these test reps, I'm just opening up an old exam, finding a question that fits that topic, and throwing it in there. That cancels with 2 of those. The 3 makes this a 9, so I would write 1/9 the integral of 3 tangent of theta minus 2 over, the 9th comes from the 3 and the 27. And then I'd have a secant. Okay, that's that step 1. Step 1 where we've done the substitution, the square root is gone, we simplified, and then we hope that we can do the trig integral. Can we do the trig integral? Well, let's simplify it. This is going to be 3. And whenever I see something like tangent over secant, I know it must simplify. Because tangent is sine over cosine. And if you divide that by 1 over cosine, it's just sine. So anyways, this is going to be 1/9 the integral of... I try to make these so that this part simplifies. In this case, it simplified a lot. And now we can integrate 1/9 negative cosine of theta minus 2/9 sine of theta plus c. There's step 2 done. Let's zoom out a little bit. I did the trig integral. And you really have to think of these as kind of 3 independent problems. The entire technique is to take something that has a square root, turn it into a trig integral, do the trig integral, and then we have one last trick up our sleeves, which is how do we return to the original variable, given that they told me, or that we decided, that tangent of theta is t over 3. So I immediately draw a triangle, right triangle, and I want the opposite to be t, the adjacent to be 3, and that means this side has to be 9 plus t squared. And the moment I write that, I now have all the ratios I want. In this case, I want cosine, which is adjacent over hypotenuse. So my final answer is going to be negative 1/9 adjacent over hypotenuse. And I'm going to do minus 2/9 opposite over hypotenuse. And so it just depends on how much I want to simplify here. Square root. I know these are big answers. As I said, this is as big as it gets this term. But it handles an important special case. This technique is not something you use very often. Primarily you use it when you're integrating equations that involve circles, since that is a pretty important special case. Now I did make a mistake now, not really an omission, which is that's not my final answer. I need to replace t with x plus 2. So if I replace that with x plus 2, then I finally have it. Okay, that's winter 2015. Let's go take a look. Winter 2015, exam 2. Oh, by parts, partial fractions, that's the one we haven't learned yet. Complete the square into the integral, that's what we just did. That's that problem. Okay, hope that gives you a little bit of a flavor of what those things are. Yes, I know 7-3 have some of the biggest problems, but they're fairly formulaic, and there are these 3 parts. Okay, I'm going to leave it at that.